Hello, everyone. Welcome to the binary episode of the Day Zero podcast. I'm Spectre. With me is Z. Today we have some ROM vulnerabilities in UNISOC, a few kernel exploits and research, and Vulns and the Crow HTTP framework. Before any of that, though, as always, we'll cover the Spot the Vuln solution, which I'll pass off to Z.
In this week's Spot the Vuln is a JWT issue, actually inspired from an issue we covered a while back in Jitsi Meet, where basically code that we have here, we've got a function verify. I'm kind of imagining that verify actually just comes from some other source, some library or whatever, but most libraries implement this in a better way to make this mistake less difficult or less easy to actually have happen. And then the lower bit of code, starting line 14, gets the JWT from a cookie, gets the server's public key, and then passes the key and the token into the verify function so that it can, check if it's a valid key. The problem is the verify function, it's taking in the key, but it's checking the algorithm just from the headers of the JWT, and that can be any of a number of algorithms. Popularly, the RS-256, that's going to be RSA and then SHA hash following it, or as like the signature. Whereas HS-256 is going to use an HMAC. And so rather with RSA, it's using a public key, and that's kind of what's expected here. I would imagine this being a developer who's writing code being like, we're only using and we're only issuing these RS-256 tokens, so all of these are just coming through using our public key. But if you crafted one, because you're just passing in that public key, it's going to use that public key as a private key to an HS-256 token. Obviously, you know what the secret key is, so you can just craft your own token, and that's where you kind of have the JWT issue. It's inspired from a Jitsi Meet issue, but generally, this is kind of just like an algorithm confusion sort of issue, so, they do pop up from time to time.
Yeah, basically, discrepancy between symmetric crypto and asymmetric crypto and the implications there. It was kind of funny. Those of you who are in the Discord might have seen the Spot the Vuln thread for this one, and I was a little wrong at first because I just started looking at this before we went live yesterday. I didn't have a ton of time, but I didn't dig into like HS-256 and put together that was like SHA-256 or HMAC-256. And somebody brought up in the thread talking about, oh, it's because you're using like symmetric crypto here, and I'm like, where do you see symmetric crypto? It's easy to read it and see like, okay, key and signature, it's obviously asymmetric, and just kind of assume it's correct without actually like thinking about it and being like, oh wait, that's actually a HMAC SHA-256, which isn't asymmetric. But yeah, it's kind of a funny issue, and it's easy to overlook. And like you said, a lot of the times where we've seen these types of issues, it's because there's a code path that's just not really used in practice, so it never gets discovered because it's just not tested for. It's not being used. So
yeah, that's where I think like most commonly you tend to find this sort of algorithm confusion issue is where you have developers who are writing the code expecting everybody just to be, basically giving the same values, following through with exactly what they expect. Like in this case, they're thinking it's always going to be public keyed ones, and thus kind of falling into it.
Yeah. All right, so we'll get into our first topic here, which I noticed Balika's in chat. You're just in time for this because you're the one who recommended this one last week. And it's from NCC Group, and details research and vulnerabilities in the UNISOC processors used in secure boot chain of Android phones. And yeah, since this is a boot ROM, it's a bit of a challenging area when it comes to research, because while second stage bootloaders or SBL are typically in firmware update packages unencrypted, the boot ROM is going to be etched into the chip. It's never really updated. What's there is there. And so typically there's no source provided for what's on these ROMs, and it's often hostile to even look at. It's not uncommon for vendors to try to like walk off the ability to mess with it or read it by burning the secure boot fuses, for example.
The ROM may have some challenges in terms of doing the research, but clearly it seems like the vulnerabilities being found here and the exploits are not so difficult.
Yeah, when we get to the vulnerabilities, we'll see it's a bit of a soft target. It's a I don't know, I guess it's a hard outer shell with a soft inner shell, because if you can reverse the ROM, there is a bunch of meme issues, basically. But yeah, speaking of burning the secure boot fuses, one of the things I mentioned towards the top of the post is they did find some devices, such as the Telecast T40, which didn't burn those fuses. So it was fairly easy to get the ROM in that case. They could just boot an arbitrary binary and dump the boot ROM with relative ease. With some other devices, though, they had to find and exploit a buffer overflow in the second stage recovery mode bootloader, or FDL1, which is where we start getting into the vulnerabilities section. So the first vulnerability they detail here is a very straightforward overflow in USB get packet for their custom USB protocol in recovery mode. It simply took a payload and didn't validate the payload length and copied it into a static buffer. And it turned out that buffer was also in or near executable memory. So code execution was pretty straightforward there. They could literally just write shellcode basically into the chip or into the bootloader to be able to get code execution. Um, from there, they reversed the boot ROM and found several more vulnerabilities in the boot ROM's recovery mode, as the validation for some of the commands was either just not sufficient or entirely non-existent, which is where we get into the meme bugs. So this was the case for the second finding here.
I mean, that first
which
one's kind of a meme bug too.
that's true. Yeah, it's not like the first one was super complicated. So the second bug here was just an unchecked write and CMD start. This was probably the funniest one in my opinion. Again, fairly simple. A user provided target address for the payload is provided in the start command, but that never gets validated. And so when the CMD receive data command is executed, you can just write attacker controlled data to an attacker controlled target address. So it's basically a free arbitrary write primitive they give you. They're very nice people, whoever wrote this boot ROM. Third finding was an out-of-bounds access due to unchecked index in the USB command dispatcher. And again, like straightforward, they take a command index from the packet and use it for a table lookup to look up the dispatcher table, see which handler they need to invoke. But that index never gets validated, so you can just go out of bounds and call something that you can control, possibly, or do whatever else. Another vuln they found was another buffer overflow in the USB data transfer function where the length wasn't validated, similar to the first issue. They just take a payload, don't validate it. There were also two other ones that were both lack of length validation, but I'm sure you get the idea at this point. The only difference with those ones was it was like an it was a out of bounds read. So could be useful for leaking data, not so much for getting code execution, but they're basically the exact same type of issues. They also found a vuln in the executable loading of the second stage bootloader, which is the most interesting vuln to me, because when you're getting into chain of trust, each node in the chain has to be able to verify the next node before executing it. Obviously, for the second stage bootloader, that'll be the ROM's job. And the key involved for doing that it's checked against is stored in efuses, so it's not easy to recover or mess with by any means. Things that are in fuses are there for like a reason. It's hard to get access to data that's locked in fuses. However, the validation that they do for the RSA is flawed. Um, and if it is flawed, then you might be able to load arbitrary code into the boot chain, and anything after that is compromised. So it's a very interesting target. The final vuln here has to do with the RSA verification of the next stage, and the fact that the boot ROM supports two certificate types, being content certs and key certs. Typically, a key cert is embedded in the second stage bootloader, and the second stage bootloader is validated against the key in fuses. The problem is, if cert type 0 or content cert is provided, they just seemingly forget to implement verification in that case. So again, kind of like with the Spot the Vuln challenge, they have this other path that they just don't use, and the logic just wasn't completed for that code path, I guess. So with a previous exploit, like by chaining with one of the previous vulns, you could try to craft a signature for an arbitrary bootloader image. They did try this, but they ran into some issues because of some other problems with the implementation for that code path, notably the fact that the hash key isn't created for the cert type 0 path. So even though it's kind of a meme and you could, in theory, forge your own signature, because of other things, it's not really exploitable. There was, though, a buffer overflow inside of the RSA implementation itself. It seems the function responsible for modular exponentiation, which performs a byte swap, did not validate the size of the key that was provided. So RSA 2048 is being used here, so it's a 2048-bit key. If you just have a key that's greater than 2048 bits, you could overflow the global signature and end buffers, which could be then used to smash the stack. Because it turns out in this memory layout, the stack is mapped after these global buffers in memory. So yeah, you could abuse this issue in the RSA implementation and get persistent code execution, because they just don't validate the key size. I mean, that one's a pretty good bug too, and is probably the best one in here. Not the funniest one. The funniest one is definitely the arb write, the free arb write, but that one's a pretty cool bug, and it's a little bit more complicated, so that might be why I find it a bit cooler too.
I kind of found it. You didn't really mention this, but they were documented here to be reusing the default UNISOC private key for signing the bootloaders that was freely available on GitHub. I was expecting you to get into that, but yeah. Also, the private key used for signing these was, available, so very secure,
Awesome.
Very hard to forge. Yeah, a lot of meme issues. Actually, this episode's going to be interesting because we start off here with these meme issues, and then our last topic's going to be dealing with CET. So
we slowly go more advanced in the episode. Yeah.
Yeah.
So yeah, a cool blog post for sure. More cool though for the type of research and the fact they're looking at the BootROM. The vulnerabilities are not interesting at all, and they don't really talk about exploitation because, well, exploitation is fairly trivial in most of the cases, if you were really looking to do it. Though, with what Z just said, you don't even need to do that necessarily because private keys leaked anyway. But yeah, cool area to research, and it is always nice seeing stuff that deals with this level early in the boot chain, because it's a fascinating area that can be really impactful if you compromise it, but it's not really looked at too much, possibly because it's just so hostile to look at. It's hard to even get the code to be able to start doing research on that level. So yeah, whenever topics involve it come up, we definitely look to cover them on the podcast. All right, so I guess with that out of the way, we'll get into the Crow HTTP framework and some of the vulns that were discovered there, by Guy and Val and Heavy. And Z, I'll let you take this one away.
Yeah, this is actually a fun couple issues. Core problem in this Crow HTTP framework is a C++ asynchronous HTTP and WebSocket framework. By the way, just don't go this route if you're going to build like a web app or something. Yeah, I get it. Apache and Nginx are both, UC, but try and avoid, vulnerable languages on the internet. Anyway, what goes on with this one is it's supposed to be asynchronous, and it kind of ends up acting a little bit agnostic to request pipelining, which is something that I guess they call it here that browsers, don't have that enabled by default, but basically it's when you can send multiple requests down the same connection without actually waiting for the responses. And so because it's not a very common feature, browsers aren't doing it by default, or if HTTP 2 has kind of better support for something similar, but HTTP 1.1 pipelining is kind of the option. So what ends up happening is the front end is reading, the connection comes in, it's reading the request, and it's creating the asynchronous job that's going to actually fulfill the request. And it'll do that no matter how many requests are coming in. So if you've got this pipelined connection, it's going to create several jobs, or 2 requests come in, it's going to create these 2 jobs on the work queue. The problem there is when it's actually tracking the state for any connection, it's treating it as though there's just one request, one response, one request, one response. It might have them following each other, keep alive the connection, but it's not really anticipating having multiple jobs working at the same time. And so they just have the flag, is it reading, is it writing? Those 2 flags are in here. Try to pull up the examples here, but yeah, it has the 2 flags there, is reading, is writing. But if you end up having 2 requests come in, getting 2 pipelined requests come in, then those workers, when they finish, they're going to go, is writing false, because it's, written its response out, even if the other one is still working. And the problem there is there's also this connection check destroy, which will destroy the connection if it's not reading and writing. So if it's done, so that can end up being called while the second one is still working, resulting in getting destroyed, resulting in use after free. And they also called out there are cases where this code will call this check destroy and then still work on the connection as without checking if it was actually destroyed or not. So it could have been destroyed and it just, blatant use after free. I did think it was kind of a fun issue just because the front end is kind of working how it should, or it is working how it should. It's just getting the request and passing it off. Um, it's accidentally supporting pipelining by being agnostic about the fact that it's even happening. So I don't know. That sort of way of introducing the bug is just kind of a fun thing to me. But in terms of the issue, also pretty stupid here.
Yeah, it's basically like an HTTP feature breaking the assumptions they have that they just supported without really knowing it. Or didn't support properly, I guess I should say. I will also mention, you talked about some of those use after frees that were like pretty straightforward, like do write static and do write general, where it would just, it could check destroy and not account for that. Though they do say they tried to find some ways to trigger those code paths and they couldn't. So that doesn't necessarily mean like those issues won't be exploitable or won't be exploitable in the future, but at least it seems like they're not super easy to hit. So it's worth calling that out. But yeah, I mean, kind of an interesting route to how the use after free happens. You need to know a little bit of the background of how pipelining works and how that breaks some of the assumptions they have. But it seems like it's a fairly straightforward UAF to trigger once you know what's going on. That said, I don't know how easy it would be to exploit it. Whenever you're talking about these server setups, especially something like an HTTP server, it's not something you're going to have a lot of control over. You might not be able to spray very easily, for example, to try to get the reallocation in for use after free. Even if you do, what are you going to put in there? You might need an info leak to chain with it. So, yeah, they don't really go into the exploitation specifics here. They just kind of stop at the bug. I mean, it's a bug report, right? So they talk about the vulnerabilities, some of the background there. They say it could potentially be exploitable, but we didn't really investigate that. Yeah, it would be cool to see if this was exploitable in some way, but I think you would probably need another bug to chain with. I doubt you could exploit this on its own. You'd be pretty blind as to the memory layout and stuff, what's going on. So
Yeah, I think it's going to depend a ton on those internal structures that I just don't know.
yeah. That said, there is a bug that was also discovered that could be used to chain with the use after free, and it was an info leak. This one is relatively stupid compared to the first vulnerability because they simply don't zero a buffer that's used to store static resources that get served. So any resource that's smaller than 16 kilobytes will just leak uninitialized data from the stack for those remaining bytes. Kind of a dumb issue, and I'm really surprised that this wasn't caught like immediately because I would expect something like this to have fairly obvious side effects, like possibly breaking images or distorting them in some way. But I don't know, maybe not. Maybe because of the encoding, it just wasn't super obvious. But yeah, I mean, fairly straightforward info leak. Well, the most simple one you can have of just not initializing the buffer before filling it with something that might be smaller in size. So
Yeah, I think with images and with a lot of things, actually, headers going to include the size that actually gets parsed.
yeah, that's true.
So
So
it's
any of the
just
tailing data is just going to be ignored.
yeah.
Yeah. Okay. So unless you actually open the image and save it and look at it, you might not notice that tailing data. But yeah, I mean, if you combine this with the previous exploit, you might be able to full chain it. Because yeah, it's to stack info leaks, especially when you're talking about up to 16 kilobytes. Like that's pretty powerful. You are somewhat reliant on what resources you can get loaded in there. You're probably not going to be able to get like some arbitrary thing in there on most targets that would be using Pro. But yeah, I mean, you could chain with the second issue, so it's kind of a nice set of finds from Guy and Val and Heavy there. All right, so up next we have a Linux kernel exploit that was posted to GitHub and was previously reported to ZDI. It was a use after free in the route for change function for route filters, and it's a neat logic bug due to how filter handles are evaluated and checked. So the README on the GitHub has the code snippet here of what's relevant. You can see at the top, for those who are watching, they allocate a filter at the top of the function, do some initialization of it, And if there's already an existing handle that has a filter, it will copy over that data and then insert it into a hash table. And then at 4, let me just go down to that. At 4, they'll remove the old filter if there was one for that handle, since it already copied all the data over. Doesn't need the old one anymore. The problem is this middle condition in the if statement at 4 here. It checks if the old filter handle is non-zero, and basically it has to be non-zero for it to remove it from the hash table. Um, However, down at 6 towards the end of the function, you'll see that they just unconditionally free the old filter, regardless of whether or not it was removed from the hash table. So, yeah, I mean, that causes a vuln because if you have a 0 handle, which you can provide, that old filter never gets unlinked from the table, but it gets freed, just leaving a dangling reference in the hash table. They use that vuln to cause a double free on the root 4 filter object, which is in the kmalloc 192 cache, which is a fairly useful cache. I think they talk about the task credentials structure being in that cache. So basically, how they exploited this was they used the dirty cred strategy. They would cause double free, corrupt the task credentials to get write access to sensitive files, and went that route, which is easier than like trying to ROP in the kernel or whatever. So yeah, not super interesting on the exploit side of things, but I thought the vuln was pretty cool because it's one of those logic bugs where it's not super obvious. You have to look at each like conditional and check like, okay, does that actually make sense? And in this case, it didn't. It's kind of like the netlink bug that I shouted out last week. Because of the condition that's being tied to the and the fact that it can be failed intentionally by the user, there's some implications there. And in that case, the implication was a tangling reference and a use after free. And double frees in the Linux kernel are pretty powerful because you can basically set up a targeted UAF on whatever you want, like a task cred. So, yeah, pretty cool exploit. The exploit code is also on the GitHub as well if you wanted to check that out. But yeah, the main thing I found cool was the bug. It's also a bug that's existed in the kernel for quite a long time. It was introduced in 3.17 and it wasn't fixed until 5.19. So it has a fairly large exploit window, though it does require user namespaces to be able to trigger the vuln. It is in a privileged area, so there is a bit of stipulation there. Though a lot of distros do allow user namespaces or expose them to unprivileged users, so it's not a huge hurdle, but it is worth mentioning, especially on some of the older kernels. Because I think namespaces came in 4.0, right? Right on
Yeah, I
that?
was actually just going to ask if you knew when namespace came in, because I don't believe they would have been there yet by 3.17 at the very least.
Yeah,
I'm
I'm
quite
pretty
confident it
sure.
was not in 3 at all.
Yeah, I'm pretty sure user namespaces came in 4. I don't remember if it was 4.0 or 4.4, perhaps. But yeah, it was somewhere in that area. So yeah, the window is narrowed slightly by that if you're unprivileged, but um, yeah, still a cool vulnerability nonetheless. All right, so we'll get into our next topic here, which is about bypassing Intel CET um, using co-op or counterfeit object-oriented programming. And we thought this topic would be cool as a launch point to talk about CET a little bit and some of the techniques around it. So Z, I'll let you get into this one, and then we can talk a little bit about CET.
Yeah, as a post, this one is I was the title Counterfeit Objects. It is hinting to a 2015 paper about counterfeit object oriented programming, which is a particular technique that was aiming at defeating CFG from it's a 2015 paper. I forget which conference exactly it came out at, but yeah, I kind of thought, even though as a post, it's not like very much here about, or there isn't much here about an actual vulnerability that we're going to find too interesting. But the idea of dealing with CET has been something, especially as CET's actually landing on some systems now, and things are being compiled with it. And it comes up as like, okay, that's the end of ROP or RIP ROP sort of positions on it. And like there are these techniques that exist to deal with control flow enforcement technologies. Both CFG, Clang CFI is kind of around. It's a software based one. CET in particular is interesting because it is a hardware based. Often it is coarse grained CFG, which just means that um, Well, so a fine-grained CFG would be like, this function call. It would know that like this call instruction can only call like a specific function or maybe a small set of them. A coarse-grained CFG is really just like you can call functions. It knows it calls a function, and it will enforce only calling some like any function. So you still have a lot of gadgets in the sense of you can call any function. And the way CET works in particular is basically with all of the calls, it implements on the call sites, it'll basically put a value there. So you can only jump to this value. And that's how it can validate that the calls are actually going to a proper call target.
Yeah, it basically like tags call sites.
Yeah, call destinations. Not implements, or well, I guess it wouldn't instrument the call site itself. Where it's going to jump to. Anyway, so as a solid post about the co-op technique. I won't go into all of the details there. There's both this post, there's the whole paper about co-op. The gist of the attack, or well, the gist of the technique here is just an option of getting something resembling arbitrary code execution while still obeying the rules of a CFG, specifically coarse-grained CFG. This is not. You might be able to pull something off or something similar off in some cases with fine-grained CFG, depending on how fine the grain is. But the gist of it is taking advantage of how C++ objects work and virtual functions specifically. Effectively, you're going to counterfeit an object, hence the name. You create a fake object, and that fake object will use, ideally, it should use like a real vtable, but it might not be that object's actual vtable. So you'll introduce a corruption. You'll have like your out of bounds read, or well, you'll have your out of bounds write or some sort of write gadget, corrupting or crafting this fake object, setting it up with a vtable, maybe pointing it to another function or whatever. And you'll craft these objects such that when a virtual function gets called on them, it references this vtable, which still needs to be a valid, or still needs to have valid function pointers, but references the vtable and calls that function out of it. I didn't explain that very well. I apologize, but let me start at the beginning, I guess, with it. With co-op, you're going to be crafting a bunch of fake objects, and you're going to have a loop. So kind of think of it like a drop attack. You have that looper function that's going to loop over some addresses and then actually make the jump based off them. Similar to here, you're looking for some gadget that's going to loop through C++ objects and call a virtual function on them. This sort of thing, does exist. In the paper calls out that it was somewhat rare, but it did exist in major libraries. They would have that code that just iterates over some collection of objects and calls a virtual function on them. It's not that expected that some generic code would probably do that. You've got a lot of collection wrappers in C++, so, you have an iterator over them. Makes sense. So, a lot of libraries do end up having it. Like, it is available, even if it's not necessarily in every small project. Generally speaking, they found it to be available. So anyway, you use that loop gadget. It's calling all of these virtual functions, and that's where your corruption comes in, where you're corrupting the vtable and just pointing it at. You're not crafting your own vtable like you would with just overwriting a vtable or vtable pointer. You're still pointing at a valid vtable, just maybe offset into it so the function that it resolves is not the right function. And from that, you're going to create your gadgets, which use the fields that the function will write to. So your input and output, rather than using registers as your key gadgets, you're really looking at using the fields of an object. So if one's going to write a arithmetic value out to whatever field offset in the gadget or in the object, another one might, if you overlay these counterfeit objects over each other, another one might use that same thing as its input for something else. And you're basically crafting these gadget chains of counterfeit objects until you can actually get to basically some function that's doing what you want with the arguments that you want. Kind of the high level overview of co-op, that it works against your coarse-grained CFG like CET, but not if you actually have any sort of signature checking in CET. And
I
that's
like to think of it. I like to think of it as kind of like a type confusion with function pointers. The code expects to be calling a function pointer that it expects to do one thing. You use your corruption to make it do another thing, which may give you some more useful form of corruption. They have like different classifications for types of overwrites you can do, types of gadgets you would look for doing things like arithmetic or stores and loads, but that's going to be a bit context specific on the target. But yeah, I like to think of it in terms of type confusion. It kind of like simplifies it down a little bit as to like what the basis of the attack is.
Yeah, the paper itself goes into kind of what the gadgets are that you need to have something that is, here it is on like page 5 of the paper. You need your main loop, that looper gadget, an arithmetic gadget, read and write, an invocation, and a write on condition. And with those, you have enough that you can basically have Turing completeness in your co-op chain. Yeah, the paper does go into a lot more and into actually finding like the looper gadget and stuff. I'm obviously skipping over that, and also actually the post itself goes into this too. Without it's also interesting, or I thought this might be a launch off point to also just talk about other CFG bypasses. And the two that kind of come to mind, at least for me, are also kind of interestingly, I mentioned this paper is 2015 Symposium on Security and Privacy. The other two papers that kind of come to mind for dealing with CFG are also 2015 papers. So that was just a good year for CFG, I guess. Or, well, a bad year for CFG, a good year for attackers.
Yeah.
So I haven't really seen any more roughly generic techniques. But the first one that did come to mind is loop-oriented programming. That one kind of similar in the sense that you need a looper gadget, which I guess isn't all that uncommon. Like Vuln mentioned, Cop or like Jop and Cop would both need some sort of looping gadget. Yeah, the idea here though is rather than dealing with like the counterfeit objects and their V tables, like the co-op attack, it's basically just saying find a loop that calls functions, corrupt the functions it could call.
Yeah,
Using call functions as your gadget.
You basically use the loop, the function call loop as like a dispatcher to go into whatever other gadgets you need to use. It's a little bit like simplified. It's like Cop, but a little bit more simplified, and you're not dealing with the faking objects. It's just using a looping gadget to go into other gadgets, basically. Yeah, as I understand it.
Yeah, no, that's exactly the idea. You have a loop that calls functions, and you corrupt what functions it calls, so you get it to go somewhere else. It's one of the more obvious things, like, yeah, because you're using call functions here, and CFG is not going to prevent you from calling call functions. Fine-grained CFG isn't going to prevent you from calling call functions. So again, this one is specifically for coarse-grained CFG. But it is another paper. Still another idea. You still need to be able to pull your gadgets out of this. And that's where I feel like law falls shorter of co-op. And that's largely just because co-op feels, I don't really have stats to back this up, but feels like you're more likely to have those smaller gadgets that actually do something useful with co-op where you have virtual functions that just do some small task versus needing to take advantage of whole functions. I don't know, just when you see object-oriented code, you're more likely to run into those small things that don't have a lot of side effects. Whereas with larger programs and just the full functions, they tend to do more. That said, that's purely just kind of an intuitive feeling of mine and not something I can back up with statistics or actually prove and, carry out any sort of proof on that. But it is another technique, at least to be aware of, in terms of just having your looping gadget calling functions, something to look for. To me, it felt kind of like a really obvious thing. Like that would be a great corruption target if you had it. And again, I think it really does depend on actually having that loop gadget. I don't remember. Sorry, it's been a long time since I've read this paper fully. But they should have looked at how common. Yeah, actually, I have the table up on screen here. Number of loop gadgets and widely used libraries and executable. So they were finding it in like libc, libsl, or in some Windows things. They were finding the gadgets. They're out there. Though they're finding, like one existed in Internet Explorer 8. So a little bit on the limited side.
And these numbers are low enough where, like, if this technique really took off, these gadgets would be killed. I guarantee it. Especially with some of these major libraries and browsers, there are like security teams and people that will go after easy to use techniques like this and kill the gadgets when they're easy to do. Which a lot of these numbers in the table that Z just showed were in like the low tens or like under 10. So it'd be pretty straightforward.
I'm trying to think. I thought Co-op also talked about like how many of their main loop gadgets they were able to find, but I don't recall where the table is, and I'm not seeing it now. You happen to recall?
I don't remember. No, I don't remember seeing a table.
Okay, maybe I'm just mistaken and it wasn't in the co-op paper. Or maybe it was just part of one of the discussions. Either way, I mean, the loop-oriented programming, it does kind of feel like yeah, so it does feel like a kind of obvious thing where you're just calling full functions. But again, it's worth bringing up because it is a bypass. It is something that you could do.
Yeah.
See here. And then one of the last techniques that kind of came up, or would come up with this, is control jujitsu, which is, again, another 2015 paper. Interesting aspect on this one is it can actually work against fine-grained CFG. Of course, because of that, it is pretty limited. But the main idea that they introduce are these ASICs, argument corruptible indirect call sites. That's kind of your key gadget. Is you need some sort of call site that's going to be calling different functions depending on the argument. So argument corruptible indirect call site. So also indirect calls. The examples that they use are they come up with one exploit against Apache HTTPD and one against Nginx. In the Apache one, they're using this these hook functions, which are effectively modules can register. I think this was on different events. They can hook certain events and then they get called. So you have this one place where even in a fine-grained setup, this one place ends up calling a lot of different functions. And so there are a lot of possible gadgets if you can corrupt the argument that's using to decide where to actually call. And potentially the arguments that's actually passing in there. So you can maybe have it where it's going down a code path thinking it's going to call with one type of object, but because of your corruption, you've turned it into something else that might execute a command you actually want. So I believe the way they actually took this was getting to system through pipe log spawn. Basically, they found a system call that was using the arguments to craft or to create a new process and ultimately calling system with that. Key thing here, though, is just starting from those points of a lot of functions being called from one place, or a lot of possible functions being called. That way, even fine-grained control, it needs to look at what the function is. So even if it is a fine-grained control flow enforcement, it's still a valid function call. Of course, you are limited to only those functions, but they did have a surprising number of like valid of these ASICs. Like, it was higher than I would have expected. Still like low tens here is one example. I'm not sure which this was on. I think this is Apache on this table. I'd have to read in the paper. Okay, no, this is Nginx, sorry. They found 36 of these call sites in total that they could have used. 27 are exercised, during like a GET request. So again, they exist. It does kind of depend on the program doing this, but this is the one that would work against fine-grained. Of course, it's also the one that's really limited in that your gadgets have to come from these functions it's allowed to connect to. And they do talk about trying to find like appropriate functions for that. They actually build a whole tool for finding these sort of call sites too. But yeah, those are kind of the few techniques, at least that I'm aware of, when it comes to bypassing CFG beyond just the obvious call hole functions, which I think usually when we come to CFG on our topics here, when we're talking about the exploitation, it's just you're ultimately limited to calling hole functions, which is true. These techniques are really just looking at places where you have a particularly large number of valid functions that you can call, places that are kind of easier to target in a corruption. So these are techniques and not corruptions in and of itself. You still need an actual corruption.
Yeah, and some of these techniques are pretty clever in the tricks they employ, but I will say my favorite CFG bypass, which is a little bit anticlimactic, is just data-oriented programming, data-only attacks.
Yeah,
I think
I
that I
totally
think that
forgot to bring that up.
yeah, I mean it's one we've talked about before, and it's kind of like I guess the go-to. Um, but yeah, I mean I've always thought that control flow, like hijacking control flow, is a little bit overrated. In a lot of the situations I've been in, it actually sucks. I'd rather just have like an arbitrary read write or something, because dealing with ROP and dealing with all the side effects and all that, it's just not fun most of the time for me. So yeah, there is data only attacks, which is the more popular one. But it is interesting looking at these techniques, and it's worth doing because um, like although it hasn't really taken off yet, CET is coming. It has been a non-existent threat. Most browsers don't use it yet. It's only recently started seeing hardware adoption. Support's been there for a while since CET is backwards compatible, but it only started getting hardware support in Tiger Lake, I believe, which was like a year or two ago. And yeah, for things like browsers, it requires a good deal of effort to make it compatible. So we're not seeing it yet, but it will come eventually, and it will be somewhat strong because CET protects both the forward and the backward edge. We didn't really talk about the backward edge, I guess, too much. But yeah, it's you can't really like ROP either because it has shadow stack. It's going to be able to check the return pointers. So yeah, with both edges protected, it is going to be somewhat strong. So looking at bypasses before CET becomes prevalent makes a lot of sense. Um, so yeah, it's cool looking at the different techniques. But yeah, personally, I think data only is probably going to be the way that the meta goes, generally for most exploitation involving targets that have it. Um,
Yeah, and
because
actually, like when we have talked about, we have kind of shown some favor towards data oriented, not just calling whole functions, like I said a little bit ago. Yeah, I don't know why. Before the show, we had talked about DOP as being what we talked about in this section. I just completely went off into all these other techniques. Yeah, DOP is kind of the main thing that at least need to be familiar with. Also get the paper here for at least advanced data oriented programming attacks. Kind of really talking about the expressiveness of uh data oriented attacks. Uh Also kind of, since I've been given the dates, everything 2015. This one was actually 2016, so it's the newest of the techniques.
yeah, and I will say like it's easy to get lost in some of the other techniques because they're definitely a lot more fancy than like DOP. Um, DOP is again like one of the ones that falls into the more obvious category. It's like, oh, okay, well if you don't want to mess with control flow, just attack the data. Um, but yeah, so it's not as fancy, but it is effective in a lot of cases. And even in situations where we haven't seen CFI, like let's say Linux kernel exploits, I guess this is a bit anecdotal, like you were saying with the topic earlier. Like, I don't really have stats to back this up, but I have been noticing with a lot of Linux kernel exploits that have been going public, most of them don't do any ROP anymore. Most of them are just like, we smash the mod probe path or something like that, which is a data only attack. You're attacking the mod probe path to get an arbitrary module loaded. You're not touching the control flow. And it's not because like CFI is in place and they can't do ROP. It's because ROP sucks compared to some of these other techniques that are just way more portable and way easier to do. Because that's another thing with ROP. Like it's not portable across versions. You You have to get gadgets for each different compilation of the binary. Um, it's just like not ideal compared to some of the other data oriented techniques, which CFG is not really going to stop. So yeah,
Yeah,
it's
and
cool to
we've
talk about
seen
CET, but yeah, the meta's already kind of shifting away from hijacking control flow anyway.
yeah, even with end user land exploits, we've been seeing more data oriented attacks. I want to say like the recent pseudo bug. I guess not recent. It's been over a year, I think now. But the last pseudo bug, one of the exploits released on that corrupted some of the logging in order to ultimately pop a shell. Well, get a privilege right, file right, and then pop a shell that way. So we've definitely been seeing more and more attacks going the data oriented route. And yeah, it is one of the benefits there is it's stable. Generally speaking, if you are if you've got an exploit, you're not really relying on having the right memory address, having the right pointers in the right places. It's data. You just, as long as you can find that data, so you end up with a lot more stable exploits also, which is just a huge benefit on any exploit, repeatability, all of that.
Yeah, that's true, and that's a good point to bring up there. So yeah, that's pretty much everything on Intel CET. Like I said, it's not like super threatening right now. I think we will see it more going forward. There does seem to be an effort on the part of an industry to get it pushed forward. Um, so yeah, it's something that's worth looking into at least before it lands and becomes generally applied across all applications.
Yeah, and I'll just say, like, if you do want to dive into co-op, I think it's Matteo Melvica. I'm not sure on the name there exactly, but this is totally a solid post about the co-op attack technique. I would recommend this over the original paper for sure. Um,
Yeah, I saw some of the diagrams. It has are really helpful.
yeah, he did a great job with this post. No, we didn't spend a lot of time on it and just use it more as our own discussion, but absolutely a solid post about the technique. And I think in the future, if data oriented isn't viable, perhaps it'll be in a case where you do have the C++ objects, and this is a option. It's gained a lot of the time. It's just you need to be aware of the techniques in order to really use them. You might not come up with them all on your own. So getting a bit of exposure to them, and it's great to see somebody else actually talking about because I don't think I've seen one post in the past. It was like back in 2018. It was before we did the podcast, at least. Was the last time I saw anybody else talk about co-op. Like it doesn't come up too often, but now hopefully listeners you're aware of it and maybe you'll be able to take advantage of it one day.
All right, so we'll get into some shoutouts. Z, I'll let you get into this first one here, which is a ZDI post on analyzing BSD kernels, and then I'll get into the one that I have.
Yeah, ZDI put out a post here analyzing BSD kernels for uninitialized memory disclosures using binary ninja. We like to shell Binja, so seeing something using Binja, this is interpreting the LLIL, one of their low-level intermediate language, one of their ILs. Jump through that in order to discover fairly simple cases of just like not zeroing a buffer before sending it back, like a copy out or copy to user. The vulnerability that they actually start off with and use for their starter case basically isn't super interesting because it really is just they didn't zero the buffer. Um, Kind of like the one we talked about earlier. So not really worth the whole topic, but they do dive into some of the Binja stuff. So if you are looking to do some analysis with Binja, I guess they use MLIL here too, which is medium level intermediate language. They have low, high, or low, medium, and high. High being more of a decompiler, which is honestly my favorite feature of Binary Ninja are these ILs. But yeah, if you want to get into the analysis, it's a decent post to take a look at. I found it fairly easy to follow. Talked about a few of the problems that they kind of had to run into or cases that they had to deal with to do their sort of data flow analysis. So yeah.
Kind of a fun shout out. The vulnerability they talk about at the top of the post, the BSD memory kernel memory disclosure and get context. This is actually one that we used on PS4 for a long time. It was a very useful info leak. Basically, it was really straightforward. They had a buffer for the context. There were certain fields that weren't initialized, and they never zeroed the buffer. So you could leak like I think it was like maybe 32 to 60 bytes or something like that, which is quite a lot when you're talking about kernel that can contain multiple pointers. So it was a very very nice leak to us in the PS4 space. Um, but yeah, pretty straightforward bug, and it makes sense they try to write a automated tooling to try to catch these types of cases because they're pretty low hanging fruit, and they can be very powerful. They can offer very powerful primitives to attackers. All right, continuing on console stuff, I figured I'd shout out the HackerOne report that some of you might have seen. The vulnerability that was used to exploit the PS5 by the Flow went public. Turns out it was a like 2-year-old vulnerability that was also used against the PS4, and somehow it just regressed and was introduced in PS5 as well. Just kind of a funny issue. I'm not really going to go into the vulnerability or anything like that. Just wanted to shout it out because I thought it was funny that they regressed that badly. That's a pretty funny bit of a meme on the fact that what was used to jailbreak the PS5 all this time was an old bug. So
It's
yeah,
definitely surprising that they had that sort of regression, didn't have any sort of regression testing for the jailbreak exploits.
yeah, especially because like Sony controls the ecosystem, right? So it's not like they're like Microsoft where they have to deal with different vendors and different hardware and different code being shipped into their stuff. This is entirely controlled by Sony. So yeah, it is a bit of a fail to have this kind of regression, but yeah, it happened. There's people that are working on exploits for this. It'll probably go public soon. It's also useful because this exploit leads to an arbitrary read write primitive, which I don't talk about PS5 or PlayStation stuff too much on the podcast, but it is a very interesting target for exploitation because it has execute-only memory in the kernel. Well, actually, across the board, userland too. So you can't just like dump kernel or dump binaries to get gadgets to do ROP, for example. It's not that straightforward. The kernel also has control flow integrity, which we're kind of talking about a little bit with CFG. It's only on the forward edge, but it is there.
You know
And
if
then on
it's
top of
like
that,
fine grained, coarse grained, or like what they're that Clang
uh,
CFI or something else.
it's a Clang based CFI,
Oh, okay.
so I believe it should be fine grained. Um, but yeah, so it has CFI, it has execute only memory. It also has a hypervisor, so you can't like patch the kernel if you have a kernel rewrite primitive. You can't you can't mess with the control registers. So yeah, there's a lot of interesting mitigations there. And this exploit is kind of like it gives you the perfect primitive for getting around some of those mitigations. So yeah, pretty useful exploit. It's worth checking out. It is an interesting bug. But it is also an old one, so yeah, I don't want to go into it too much on the podcast, but yeah, wanted to shout it out regardless. So, all right, Z, unless you have anything else to add, we'll go ahead and wrap up the show.
Nope, I have nothing else to add.
All right, so that's everything we have for this week. As always, thanks everyone who tuned in. VOD will be up on YouTube and other platforms tomorrow. Links for everything and summaries can be found on our site at day0sec.com. Remember to follow our Twitter and join our Discord if you want to see notifications of when stuff goes up or streams or whatever, or just to participate in the Spot the Vuln challenges we have every week. And yeah, with that said, we'll see you guys next week on Monday for the Bounty episode and Tuesday for Binary, and we'll see you then.